So we now come to the actual proof of Urysohn's lemma, and what we will prove the following statement, that space X is normal. This implies that for any closed set K and an open neighborhood U of K, so this means that K is a subset of U, there exists a continuous function on X, let's call it F, and which takes values in 0, 1, in the closed interval 0, 1, such that we have that the indicator function for K is less than or equal to F of X, which is less than or equal to the indicator function for U. So we have already seen that this is equivalent to saying, so this statement, the last statement, is equivalent to saying that for any pair of disjoint closed sets A and B in X, there exists a function, there is a continuous function, so let me write continuous here, a continuous function F from X to 0, 1, which separates A and B, meaning that F restricted to A is identically 1 and F restricted to B is identically 0. So and we have already seen that if you assume this statement here, then we have seen that X is normal. So the reverse implication is already done. So in fact this is an equivalence. So the reverse implication is done and we only need to show the forward implication. So let us prove the forward implication. So we will only need to show the forward implication. And so now we will use the equivalent characterization of normal spaces that we saw before. When you have a point, a closed set X and an open neighborhood of that closed set, then there is a intermediate open neighborhood of that closed set whose closure lies in the given open neighborhood. So we will use that characterization for normal spaces. So recall that X is normal if and only if given any closed set K and an open neighborhood U of K, there exists an open neighborhood V of K, such that we have K is a subset of V closure, subset of U, and we will use this this equivalence to prove the forward implication of Urysohn's lemma. Okay, so let's see how that works. So in the first step, so in step 1, so we have an iterative process again, and in the first step we let K1 to be equal to the given closed set K, and U0 as the given open neighborhood U of K. So K is in U open, and the beautiful idea of Urysohn's lemma is to index is to find a sequence of closed and open sets indexed by something called the dyadic rationals. So this is our first step, and I will explain what is a dyadic rationals. But let me already put the second step before I do that. So in the second step, because of this property here, so there exists an open neighborhood which I call, so V is the open neighborhood, but I will denote it as U half. Okay, so U half is the open neighborhood V, which is between K and U, and whose closure lies inside U. So such that K, so here I am going to use the indices that I use in the first step. So K1 is a subset of U half, which is a subset of U half closure, and this is a subset of U0. And here I will denote this U half closure as K half. So this is K half. So this is the same as saying that K1 is a subset of U half, which is a subset of K half, and this is a subset of U0. And now, so what we have done here is to take the unit interval 0, 1. In the first step, we indexed our middle set as V half. So we took the middle point of 0, 1. And what we are going to do in this next step is to further subdivide the first half and the second half, and we take 1 by 4 here and 3 by 4 here. So and to do that, we will use the pairs of closed and open neighborhoods. The first one is K1 U half, and the second one is K half U0. And we will put the lower half of the subinterval, so it's the 0 half. So you will put the index 1 by 4 here and 3 by 4 here. So let me write this more clearly in the next step. So step 3. So now there exists open sets U 1 by 4 and U 3 by 4, such that you have K1, this is a subset of U 3 by 4, this is a subset of U 3 by 4 closure, and I will denote this as K3 by 4 as before. And then again, this is a subset of U half, and similarly we have, this was already a subset of K half, but now we have another pair which is now U1 by 4. So U1 by 4, U1 by 4 closure, which is again K1 by 4, and this is a subset of U0. So I'm going to write it more clearly again once more. So K1 is a subset of U3 by 4, which is a subset of K3 by 4, which is a subset of U half. Then we have K half, then we have U1 by 4, then we have K1 by 4, and then we have U0. Okay, so this is what I meant by putting 3 by 4 here and 1 by 4 here. So we are going to repeat this process again and again, and these kinds of subdivisions of intervals in half, starting from the midpoint of 0, 1, which is half. So this is called, this sequence of rational numbers they are called dyadic rationals. So these are called dyadic. So let me give this as a definition. Dyadic rationals. So these are, of course, rational numbers of the form m by 2 to the power n, where m lies between 0 less than m and it's less than 2 to the power n. So of course you can have here less than or equal to sign as well. So rational numbers of this form. So if you have, for example, if n equal to say 1, then you have 0 less than equal to m less than equal to 2 here, and so the only possibilities for this is 0, half and 1. And this is the first picture that we drew in step 1. Okay, if n equal to 2, then we have 0, 1 by 4, half, 3 by 4, 1. So here n lies between 0 and 4 now. So this was the second picture we drew with 1 by 4, then we had half, then we had 3 by 4, then we have 1, and so on it goes. And we put the, so let us concentrate here. You have half here. We put the higher dyadic rationals to the left and the lower dyadic rationals to the right. Okay, so we have put 3 by 4 to the left and 1 by 4 to the right. So whenever there is a higher dyadic rational, we put to the left, and a lower dyadic rational, we put the pair of open and closed sets to the right, and so it goes. So this is an iterative process, and in general we get a collection of open and closed sets indexed by the dyadic rationals let's call it D, such that we have that the any closed set KQ is a subset of UQ prime if 0 is less than or equal to Q prime is less than Q, and this is less than or equal to 1. So for example, if we have Q to be 3 by 4, Q prime to be half, so we have Q prime less than Q, and then we have seen that K 3 by 4 is a subset of U half. So this was in step 2, and similarly we have this inclusion for all pairs of dyadic rationals Q and Q prime, such as this. On the other hand, we also have, so in fact this is a consequence. This is a consequence of putting sets indexed with higher dyadic rationals to the left. So as I explained before, we put the higher ones to the left and the lower ones to the right. And similarly we have that UR is a subset of KR prime, 0 less than R prime less than R less than 1. So and of course we have a UQ is a subset of key q for all q in D. So here of course R and R prime belong to D, and here also q and q prime are in D. So we have these three important properties for the pairs of closed and open sets, and we will use the fact that the dyadic rationals are dense in 0, 1. So we will use that D is dense in 0, 1, and in fact for any two dyadic rationals, say q1 and q2, there exists a q3 lying in between these two things. So this is something like the second property of a linear continuum, and we will exploit this property for dyadic rationals. And now we are ready to define the function which will be sandwiched between the indicator function of our closed set, given closed set K, and the indicator function of the open set U. So this is step 4. So we define a function f from x to the closed interval 0, 1. So for any x which does not belong to, so for any x which belongs to K, we put f of x equals 1. Okay, for any x in U complement, fx is equal to 0, and so the only part is where you have to define it for U minus K. So for any x in U minus K, and this is the most interesting part, so this is defined as f of x is equal to the supremum of all the dyadic rationals in D intersection 0, 1, such that x belongs to the open set UQ. And with this definition, it is easy to check. It is easy to check with this definition that we have automatically that the indicator function of K is less than or equal to the indicator function of f, and this is less than or equal to the indicator function of U. So the only thing that we need to show is that f is continuous. So this is the main part of the proof. Step 5, we claim that f is a continuous function. So to do this, we will show that two things. So first is that the set of x in x such that f of x is greater than a given number alpha between 0 and 1. So for alpha in 0, 1, this is equal to, so by the way, this is nothing but this inverse image of the open set alpha 1, right? So it is the inverse image of alpha 1, and this is open in the subspace topology. And this is equal to the union of all over all dyadic rationals Q greater than alpha of the sets UQ. And similarly, we have that the set of points in X such that f of x is less than alpha, and this is the inverse image of the open set 0 alpha open it at the end alpha, and this is equal to the union over all dyadic rationals q less than alpha of the complements of kq. So once we show this is enough. So 1 and 2 imply that f is continuous, because all subsets, the collection of all subsets of the form, since the collection of all subsets of the form 0 closed alpha open at alpha and alpha open at alpha closed 1. So this is open at alpha. So these two kinds of sets is a subbasis for the subspace topology. Subbasis for the subspace topology on 0, 1. So it's enough to check a continuity for subbasis elements. So therefore, so note here that this is a union of open sets, countable union actually. So the dyadic rationals are countable. Okay, so countable union of open sets, and similarly this is also a countable union of open sets. So now let us prove these two claims 1 and 2, and then the proof will be done. So let us prove the first claim. So claim 1 is that the inverse image of alpha 1 is equal to the union over all dyadic rationals q uq. So let me denote this set as A and this set as B. So we will prove that A is a subset of B and B is a subset of A. So to prove that A is a subset of B, let x belong to A. So this is the same as saying that f of x is greater than alpha, and if we replace fx with its definition, so we have q in 0, 1, then we have x in uq. This is greater than alpha. So if you just see in a picture, so you have alpha here and the supremum lies somewhere here. So this is, so if this supremum is lambda, then this lambda lies somewhere here, and so this means that there will be a point, let's call it q naught, which lies between alpha and lambda. So this means that there exists a q naught in D intersection 0, 1 such that alpha less than q naught less than lambda and x belongs to u q naught. And so we have found an alpha q naught greater than alpha for which x belongs to u q naught. So this means that x belongs to the union of all the uq's over the dyadic rationals greater than alpha uq. So this means that x belongs to B. So therefore we have A is a subset of B. And now to prove the reverse inclusion, so now let x belong to B. So this is the union over all uq's, q in D. So whenever I take D, I mean D intersection 0, 1. Okay, so dyadic rationals of course lie in the closed interval 0, 1, but I am taking the open interval 0, 1 here. So yeah, so this means that x, so there exists a q, there exists a q1, let's call it, in the intersection 0, 1, says that x belongs to u q1, and so of course and we have q1 greater than alpha. So this is the just using the union membership in a union. So x belongs to u q1 for some dyadic rational q1 greater than alpha, and in this case we again have here alpha, and we have found some q1 a dyadic rational which is greater than alpha, to which x, so such that x belongs to u q1. So this means that automatically, this means that the supremum over all the dyadic rationals in 0, 1 such that x belongs to uq is going to be greater than alpha, because one of the members is greater than alpha here. Okay, so here q1 belongs to this set, therefore the supremum is going to be strictly greater than alpha, and this means that f of x is greater than alpha, and this means that x belongs to A. So this means that B is a subset of A, and so we have shown that, so A is equal to B, so proving the first claim. And now let's prove the second claim. So this is on the left side we have the inverse image of the set 0 alpha, and on the right hand side we have the union over all q less than alpha now, so all q in the dyadic rationals in 0, 1, and with kq complement. So again, let's call this set A and let's call this set B, and first let x belong to A. So this is the same as saying that the supremum over all q in D intersection 0, 1 such that x in uq is strictly less than alpha, and so if you let lambda to be this number, so you have here again alpha, and here this is lambda which is f of x. Okay, so lambda is f of x, and now this means that x does not belong to uq prime for any q prime which lies between 0 and which lies between lambda and alpha. So any q prime belong to lambda alpha. So lambda less than q prime less than alpha. Of course q prime is in the dyadic rationals. So this is simply because we are taking the supremum of all these q's such that x belongs to uq, and so if you take a set uq prime for which the index lies greater than lambda, then x will not belong to uq prime, because if it did, then the supremum will be greater than lambda, right? So we have this, and now choose. So now we are going to use the properties of the closed sets that we had. So since q double prime was a subset of uq prime for any q double prime greater than q prime, of course this is going to be less than 1, this is going to be less than 0, so less than or equal to 1. So we have this property that if you have a higher dyadic rational, so the closed set with the higher dyadic rational index will lie to the left, right? So we have kq double prime is a subset of uq prime for any q prime q double prime greater than q prime. So now so choose any such q double prime. So this is a dyadic rational such that we have lambda less than q prime less than q double prime less than alpha. So we have found a dyadic rational q double prime. So q double prime lies somewhere here, which lies between q prime and alpha, and this means that x does not belong to q double prime. So we have found a dyadic rational less than alpha to which x does not belong to q double prime. So this is the same as saying that x belongs to q double prime complement, right? And this is what we want, because our set B is the union of such things. So this means that x belongs to B, and so A is a subset of B. And now for the reverse inclusion, so let x belong to B. So this means that there exists a q less than alpha, q of course belong to the dyadic rationals, such that x belongs to kq complement. Let me denote this q prime, and since q double prime is a subset of kq prime for any q double prime greater than q prime, of course both are dyadic rationals, then we have this means that x also belongs to the q double prime complement for any q double prime greater than q prime. So this means that x does not belong to q double prime for any q double prime greater than q prime, and this already means that x belongs to A. So so you have this, so let me redraw it. So you have here alpha, and you have found a q prime for which x does not belong to kq prime, and x also does not belong to any of the uq double prime which lies between q prime and alpha. So this means that the supremum of all the q's in the dyadic rationals says that for which x does belong to uq is going to be strictly less than alpha, and this means that fx is less than alpha. So x belongs to A and B is a subset of A, and so we have shown that A equals to B. So we have shown the two claims, and this completes the proof of the continuity of the function f, and also the proof of the Urysohn's lemma for us.